everyone, welcome to Depth First. We will delve into the depth of the algorithm behind reversing a linked list. This is a popular Leetcode question and can be applied to solving other linked list problems. A good understanding of the linked list data structure is necessary. If you need a refresher, I have included a link to my linked list video in the description. So this is the question. Given the head of a singly linked list, reverse the list and return the reversed list. This is the linked list that we are provided as part of the question. We are given a variable called head, which points to the first node of the list. The first node points to the second node points to the third node points to the fourth, and the fourth node points to the fifth, and finally the fifth node points to none. Our objective is to traverse each node and reverse the direction of where it points to, beginning from the head. Upon reversing the nodes, we must return the new head, which is the fifth node. There are two solutions to this problem, iterative and recursive. Let's first take a look at the iterative solution. Okay, so let's now examine the process. We need a variable to track the node that we are currently processing. We'll call this variable cur, which stands for current. For the ease of understanding the algorithm, let's just assume it points to the second node. Also, let's assume that the node before the second node has already been reversed. So let's consider our goal. We want to modify the next value of the current node to point to the previous element that we just encountered, which in this case is 1. Now this requires us to have a means of tracking the previous node. We'll track it using the variable pnode. However, if we just go ahead and change the next of the current node to point to the previous node, we'll end up breaking the link to the rest of the list. Therefore, we need to maintain a record of the next node that follows the current node. This variable will aid us in traversing to the next element in the linked list. So, as I just explained, we'll create a variable named cur that will point to the first element in the list. We will also create another variable named pnode and initialize its value to none. We will iterate through all the elements using the cur variable. In each iteration, we'll create a variable named nNode and set its value to the next element of the current node. Afterwards, we'll change the next value of the current node to point to the previous node. So this change is not concerning to us anymore, as we have already stored the reference to its next node. We will then update the previous node to point to cur. And now we can update cur to point to nNode. We'll continue to repeat this process in a loop until cur is not equal to none. Moving on, here's what the loop looks like after the third iteration, the fourth iteration, and finally the fifth. As depicted in the animation, the loop terminates when cur reaches none. Once the loop ends, we will return the new head by returning pnode, which now points to the new head of the linked list. So here is the code for reversing the linked list. It includes the initializations, the loop invariant, and the loop termination. Please also note that this code handles all the edge cases, including the scenario when the linked list has only one node or when head is passed as none. I encourage you to verify this by testing the code yourself. Alright, so let's now discuss the time and space complexity of the iterative solution. Assuming the linked list has n nodes, reversing the list requires iterating through each node one by one. Therefore, the time complexity of this algorithm is O of n. The space complexity of this algorithm is constant, as it only requires 3 additional variables and does not allocate any extra space. Okay, it's time to move on to the recursive solution. Now, a recursive solution involves solving a problem by solving a subproblem of the same problem. Let's try to determine what the subproblem is in this case. Let's consider a scenario where our linked list has 4 elements and we need to reverse it. The subproblem in this case will be the list containing elements 2, 3, and 4. In solving recursive problems, what I've found most useful is that you have to imagine that the function that we are writing already exists. You need to have faith that it will perform the task correctly, such as reversing the list for us. We'll call the reverse function on the subproblem or the sublist. The new head will now be at node 4 and node 2 points to none because this is the last node of the subproblem. What do you think? Can we solve the problem now? Well, we've reversed the sublist as part of solving the problem. But do recall that 1 still points to 2. So in order to solve the entire problem, we need to change 2 to point to 1 and subsequently change 1 to point to none, making 1 the last node. But how do we find out the last node of the subproblem? So if you think about it, the last node of the subproblem is node 1's next element, which is 2 in this case. So we'll first change 2's next to point to 1, and then we'll change node 1's next to point to none. Our problem is solved and we can send the new head back all the way up the call stack. So that's the code for the recursive solution. The first statement is the base case where if we've reached the end of the linked list or if head is passed as none, we return back the node. We'll call the reverse function and pass in node.next as the subproblem. This will return us the head of the reversed sublist. We'll get the last node from node.next. We'll then set the next of the last node to the node itself. And then we'll set node.next to none. We'll send the reversed list head all the way back up the call stack. Moving on, let's now discuss the time and space complexity of the recursive solution. When trying to analyze the time complexity of a recursive algorithm, it's very important to ask oneself how deep the recursion will go. For a linked list containing 4 elements, the subproblem would be to call the reverse function for the list with 3 elements, which would then call the reverse function for the list containing 2 elements, and so on. The depth of the recursion is proportional to the number of elements in the linked list, so the time complexity will be O of n. The space complexity is also O of n because for every call to the recursive function, the call stack grows. In the worst case scenario where we traverse the entire linked list, the call stack will be n deep, resulting in an O of n space complexity. If you are unfamiliar with the concept of recursion, I strongly encourage you to learn more about it. While grasping the intuitive workings of recursion can be challenging, as it was for me, I have included links in the description to help you better understand recursive techniques. Thank you for taking the time to watch this video. If you have any questions or suggestions, please feel free to leave them in the comments section. I'll do my best to respond to them. If you found this video helpful, please consider giving it a like, subscribing to my channel, and sharing it with others. Thank you.